Hi, today we will present our project Research and Development of Autonomously Controlled Wings for Reusable Solid Fuel Model Rockets. My name is Netichon Kamali and my partner name is Chupung Vibun. Have you seen them before? Of course, these are rockets, and rocket or space technology and knowledge is a very valuable resource, though it is still very underdeveloped in Thailand. These are all examples of space product or space developments. We want to learn it and develop something, so we joined Kansas 2022 competition in Thailand, and we found an unexpected failure from Kansas. That is, a rocket flew into the sea, making it unrecoverable. So we're trying to find a new solution, which is dual deployment. Dual deployment doesn't really work because we can't control it. So we have to find another new solution, and we found this. SpaceX. SpaceX used a liquid-fueled rocket engine to do a boost back burn and then land their craft back to the landing complex. But we can't do that because we use a model rocket which is smaller and only can house a solid fuel rocket. So we try to replicate the method using a new invention, which is we combine two of their methods into our new method using glided wing and then use a parachute right before touchdown to slow down our craft right at the base. Next, we will talk about our rocket and our building process. Our rocket composes of three main parts, which is flight computer, guided fins, and rear wings, which will make most of the lift, and a parachute bay. Our wings and fins are designed according to aerodynamics, and then we design our flight path accordingly. And then we created it in Fusion 360, making it into a 3D model and then slice it in Prusa slicer and printed it using 3D manufacturing procedure. Our left is our design drawing of the mechanism, and our right is the 3D model to prototype of our rocket. And we test the wing in ANSYS Fluent to verify the characteristic of our fins and wings. This is our simulation data and our profile for the wings. Next, we'll hand out the mic to Chupung Vibun to talk about the control system.
And before we can control the rocket using flight computer, first have to know where our rocket are. But how do we know where we are? In order to obtain position, we use GPS module and get tracked by satellite to calculate displacement from launch pad, then calculate the flight path and feed data to main control loop called PID loop. But why are we using the PID control? Because even though we know how rockets should orient in order to glide along, follow the appropriate flight path, but we don't actually know how to command steering fin accurately, and the PID deal with that job very well. What PID do is to set up orientation, set point, and command steering fin, and then measure the error from set point and feedback to control loop to reduce error. And due to that process, our rocket can orient approximately to the desired orientation from calculation. Like this is the equation of PID control. And here, this is the result of PID control in simulation. This is the result of regular PID control. By varying the PID parameter and the response is changed. And here's the result of our roll simulation. As you can see, the result graph rocket try to orient to set point angle and manage to maintain it. That means our control system worked, but I have to say that we didn't simulate the displacement yet, and that's the end of the software part of flight computer. But we also need the hardware, so we use the TC 4.1 microcontroller board and connect sensor to the board. And this is our wiring diagram. Here is a pre-alpha model while we connect the jump wire together directly to breadboard, but it kind of look messy, so we improve it by using the perf board and we soldering it. And for our future plan, we tend to develop real-world testing model method design. And we build test land structure from aluminum profile. And that's all for our presentation today. Thank you.